Hey everyone, today we are diving deep into the world of embedded systems. We're going to map out exactly what you need to know to be a top-tier embedded engineer by 2026. We'll cover everything from the skills that never change to the modern workflows that are completely flipping the industry on its head. Let's get right into it.
So, embedded systems are hitting a wall, a complexity crisis, really. The amount of software in our cars, our planes, you name it, is just exploding. And this number right here, it says it all. The average car is expected to have 650 million lines of code by 2025. I mean, that's just a mind-boggling jump, and it's a trend we're seeing across the board.
In this explosion in complexity, well, it creates huge problems, mainly because the old way of doing things just doesn't work anymore. We're talking about massive bottlenecks in hardware testing, where teams are stuck waiting for weeks just to get feedback on their code. Or what about those inconsistent build environments, where the code works perfectly on one developer's machine but mysteriously breaks on another? These aren't just little annoyances. They bring innovation to a grinding halt.
Okay, so before we jump into all the newfangled solutions for these modern problems, let's take a step back and get grounded. Because no matter how much the tools change, there's a bedrock of fundamental skills that is still absolutely essential for any embedded systems engineer. This is your core. This is the foundation everything else is built on.
First things first, you have to know C and C++. It's just non-negotiable. C is really the language of hardware. It gives you that super fine-grained, bit-level control over registers, memory, all the peripherals. You need it for low-level drivers and kernels. C++, on the other hand, is how you manage all that growing complexity we were talking about. It lets you build these clean, modular, object-oriented firmware architectures, so you can create really sophisticated apps without getting totally lost in spaghetti code.
Now, what's really cool about this is how it breaks down your choice of microcontroller. The ARM Cortex-M, which you'll find in the massive STM32 family, is really dominant in the professional world for a good reason. It's super scalable and built for rock-solid real-time control. But a modern engineer needs more tools in their belt. If you're building an IoT device, the ESP32, with its built-in Wi-Fi, is often the quickest way to get a connected product. And if you need to create some kind of custom communication protocol, the RP2040's programmable I/O, the PIO, is an absolute game changer. It's like having these tiny little state machines that you can program to handle super high-speed I/O without bogging down the main CPU.
You know, as these systems get more complex, that old-school while-one super loop, it just doesn't cut it anymore. You've got multiple things that need to happen at once. You're reading sensors, you're updating a display, you're talking over a network. This is exactly where a real-time operating system, or RTOS, becomes absolutely indispensable. Think of it like the conductor of an orchestra. It manages all these different tasks at the same time and makes sure that the most critical jobs always finish on time, every time.
And look, you can't just use an RTOS, you have to really master its core concepts. That means you have to deeply understand task scheduling, how the system decides what code runs and when. You have to know how to use all the tools for inter-task communication, like queues and mutexes, so you can pass data around safely. And you have to get a handle on resource management so you don't have different tasks fighting over the same piece of hardware. This knowledge is what really separates the beginners from the experts.
All right, so with that solid foundation in place, how do we actually go about solving that complexity crisis we mentioned at the beginning? Well, we shift to a whole new paradigm. We're basically borrowing a page from the web development playbook and bringing DevOps principles into the world of embedded systems.
So here's the crucial change. The era of, well, it works on my machine is officially dead. Professional teams today just cannot afford the delays and the bugs that come from manual builds on a local computer. Instead, we use standardized continuous integration and continuous delivery, CI/CD, pipelines. By using tools like Docker to create these self-contained build environments, we can guarantee that every single build is consistent, repeatable, and completely traceable.
And this right here, this shows the modern way to do testing. Instead of writing a bunch of code and then waiting weeks for a physical prototype to show up, we create what's called an automated testing funnel. We start with software in the loop, running tests on a virtual simulator. The feedback is incredibly fast. Then we move to processor in the loop, testing on a representative chip. And finally, we get to full hardware in the loop, testing on the actual production hardware. This layered approach lets us catch bugs way earlier, way faster, and a whole lot cheaper.
Now, this modern workflow doesn't just happen by magic. It's powered by a specific set of tools. We're using Git for version control, of course. We're using GitLab CI or GitHub Actions to automate our pipelines.
Docker is giving us those consistent build environments. Tools like Renode let us do some really powerful simulation. And Python? Well, Python is the glue that holds it all together. The scripting language we use to automate everything from test sequences to analyzing the data.
Okay, let's switch gears and talk about something that's gone from a nice-to-have feature to an absolute must. With billions of devices now connected to the internet, security isn't some afterthought you tack on at the end. It is a critical mandate that has to be designed in from day one.
Real device security starts right here with a hardware-based root of trust. You can think of it as the ultimate security anchor for your entire system. It's a small, unchangeable piece of code or hardware that is trusted by default. Its only job is to check that the very first piece of software that runs when your device boots up is authentic and hasn't been messed with. If you don't have a solid root of trust, then everything else you try to build on top is basically built on sand.
So that root of trust, that anchor, it supports all the other pillars of device security. Secure Boot uses it to validate the firmware every single time the device turns on. Secure firmware updates use cryptographic signatures to make sure that any update coming over the air is legit. Secure communication protocols, like TLS, protect your data when it's flying across the network. And finally, resource isolation uses features in the hardware to build firewalls right inside the chip, preventing one buggy or malicious part of your code from taking down the whole system.
And this is why all of this matters right down at the code level. You can have the best security architecture in the world, but it can all be brought down by one simple bug. A classic buffer overflow, where you accidentally write past the end of an array, isn't just a stability problem. It's a gaping security hole that an attacker can use to take over your device. That's why disciplined, secure coding practices are an absolute non-negotiable skill for any modern embedded engineer.
Okay, we've covered the core skills, the modern workflow, and the security mandate. So now let's tie all of this together and see what it means for your career and the future of the job market. What do the numbers actually say?
The demand for skilled engineers isn't just growing, it's absolutely surging. The U.S. Bureau of Labor Statistics is projecting a 25% job growth for software developers over the next decade. That's way faster than the average for all other jobs, and it translates into hundreds of thousands of new positions. The opportunities are just massive for people who have the right mix of skills.
And as you can see right here, specialization really pays off. Having a solid embedded foundation is essential, of course, but engineers who build up expertise in these high-demand areas see a real impact on their paycheck. Things like integrating AI and machine learning at the edge, becoming a specialist in security engineering, or mastering cloud connectivity for distributed systems, these are the skills that command serious salary premiums in today's market. And if we look even further down the road, there are a few key trends that are going to change how we work all over again. AI is starting to creep into our tool chains, helping us generate driver code and test scripts just from plain language prompts. The industry is taking a serious look at memory-safe languages like Rust to just eliminate whole categories of bugs at compile time. And our IDEs are getting way more powerful, integrating everything from code generation to on-chip debugging into one seamless workspace. So, what's the big takeaway here? The world of embedded development is moving faster than ever. It's growing from just a core of C programming to include modern DevOps workflows, strong security architectures, and forward-looking tech like AI and Rust. The future is literally being built, line by line, on these tiny, powerful devices. So the real question you should be asking yourself is, are your skills built for that future?
If you like this one, the YouTube algorithm says you're going to love my other videos, so go check them out.